Now,
I was going to give my introduction. All right. Great. So great. Our first talk of Tuesday is by Paul Wedrich from Max Planck in Bonn and the University of Bonn. And the title of his talk is Invariants of Four Manifolds from Khovanov-Rozansky Link Homology.
Yeah, thanks a lot for the introduction and the invitation to speak here. It's an absolute pleasure to be able to present this work to a group of actual topologists. And I'd love to get your feedback on this. So let's get started. So this is joint work with Scott Morrison and Kevin Walker. It's based on a preprint that we wrote 2 years ago, appeared in July 2019. And yeah, let's just get started. So the motivation for this work was the question how Khovanov homology extends to other ambient manifolds. So a priori, this is a link homology theory for links in R3 or the 3 sphere and certain cobordisms between them. And it's been for a long time an important question how to extend this. There are different ways one could try to extend such a thing. And I want to follow the following hints for the purpose of this talk. So the first hint is that in such an extension to other ambient manifolds, an important role should be played by the fact that Khovanov homology, at least in certain constructions, is properly functorial under link cobordisms embedded in 4-dimensional space. So not only do you get an invariant of links that may take the form of a vector space or an abelian group, but also you get maps, linear maps or group homomorphisms associated to link cobordisms. That's the first hint. The second hint is that there already are extensions of Khovanov homology to other ambient manifolds. And the one that I want to focus on here is due to Rozansky, and then it was generalized by Mike Willis. And it works for null homologous links in connect sums of S1 times S2. And the third hint that I want to follow is that Khovanov homology is known to be sensitive to smooth surfaces in the four-ball due to the famous work of Jake Rasmussen. Okay, and this motivates the following perspective. Khovanov homology should be thought of as an invariant of links in the boundary of the four-ball. Okay, that's the perspective that I want to take for this talk. And starting from this perspective, you could now hope that there exists an extension of the following type. To 4 manifolds, compact-oriented 4 manifolds, with a link in the 3-manifold boundary, you would assign chain complexes. And then in the particular case of the 4-ball with a link in the boundary, you just recover the ordinary link homology. And then you could hope that this extends downwards, like an extended TFT to 3-manifold, where it would assign DG categories, and then down, 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 all the way until you hit the point. And to the point, it would associate some kind of 4-dimensional category. So if something like this works, and I wouldn't claim that we're there yet, then this would exhibit Khovanov homology as somehow the main ingredient for a partially defined extended 5-dimensional field theory. I say 5-dimensional because topological field theories typically associate numbers, something like numbers, to top-dimensional manifolds. Here on the 4-dimensional level, we already associate chain complexes. So you're already somehow 1 dimension down from this top level, and then it goes down. And I say it should be a partially defined 5-dimensional field theory because it won't be defined on all 5 manifolds. Okay, so that's the kind of general picture that this talk and the work that it's based on is motivated by. And in this talk today, I want to show you a few steps that go in the direction of somehow realizing this picture. And then the outcome will be a 4-manifold invariant. So an invariant for compact-oriented 4 manifolds with a link in the boundary that takes the form of a vector space with some gradings. And then along the way, I'll tell you about many open questions regarding this. And then there will also be the following talk by Ikshu Nathalov, and he will tell you about computations with this four-manifold invariant. Okay, so to motivate what kind of four-manifold invariant that is that I'm going to show you, I have to start at in dimension 3. So I want to describe somehow the analogous constructions in dimension 3 to warm up. And there are 3 mathematical concepts which are very closely related and which will guide us to these manifold invariants. And they are, on the one hand, link invariants, and second, higher categories, and third, manifold invariants. And the starting point will be link invariants, and specifically for the purpose of this talk, the GLN link polynomial. So I denote that by Pn, and it is a function that assigns to framed oriented links some Laurent polynomials in a variable q, and it is governed by skein relations. So the linear relations that relate the polynomials of links whose diagrams differ only in a small region. So for example, here, consider a diagram where you see a positive crossing, then you can relate the invariant of this to the invariant of the link with a diagram where you have negative crossing there instead, or this parallel resolution. And similarly, there are rules that allow you to somehow relate invariants of links that have blackboard frame diagrams that differ by such a kink removal. And under disjoint union, this invariant is multiplicative. So this is a link polynomial that is somehow completely determined by local relations. And whenever you have such an invariant, you can ask whether it extends to a tangle invariant. And here the answer is yes. And the conceptual home for these tangle invariants is the ribbon category of finite dimensional representations of the quantum group associated to GLN. Maybe I should say here it's somewhat important to work with GLN because I mean, sometimes people say SLN, but if you want to work with SLN, then you have to get some fractional powers of Q, and for categorification purposes, that's inconvenient. So we want to work with GLN instead. And I should also say that if you set n equals to 2, then this polynomial is just recovers the framed version of the Jones polynomial. So something very familiar and famous. Okay. Yeah, so back to this. So we have this quantum group associated with GLN. One can look at finite dimensional representations of that forms a graded monoidal category with duals and with certain compatibilities. And this is where tangle invariants live. The picture to keep in mind is the picture on the right. So here you see a tangle. The components of the tangle are labeled by objects of this categories, certain representations. And then the famous Reshetikhin-Turaev construction allows us to interpret such a tangle diagram as an intertwiner from the representation that you read off at the bottom to the representation that you read off at the top. And the fact that this is a ribbon category just encodes that somehow the morphisms that you can assign to such the morphisms you can assign to such tangle diagrams respect the kind of topological kind of isotopies on the tangle. On the level of tangle diagrams. So in some sense, this category has the same symmetries as tangles do, and that's why you can find tangle invariants in this category. Okay, and then the third side are these manifold invariants that are called skein modules. Whenever you have a ribbon category, you can form a skein module for oriented 3 manifolds. So let's take such an oriented 3 manifold M3, and we may also choose a set of points in the boundary. And then one defines the skein module of M with relative to the set of boundary points by first constructing a free module over the ring of Laurent polynomials in Q, spanned by framed oriented tangles embedded in the 3 manifold with the prescribed set of boundary points. And then one mods, so this is a huge space, and then one mods out by local relations. So first of all, whenever 2 such tangles are isotopic, then you consider them equivalent here. And you also mod out by local relations. And the local relations that you mod out by in this case are exactly the local relations that are satisfied by this polynomial Pn. Okay, and that shrinks the size of the skein module. Typically, in this case, it will still be infinite dimensional. If you change the ring here, then you can sometimes get this finite dimensional, and there was recently a lot of work on this. But here I want to stay in this setting. And there are lots of variations of this. So you can allow these boundary points. You can allow these boundary points to be labeled by such representations. And then these skein modules have some nice gluing properties. And so what I would like to convince you of in this talk is that these three different concepts, these somehow locally determined link invariants, the ribbon category, RepUQGLN, and the concept of the skein module manifold invariants are somehow extremely closely related. And if you somehow understand one very well, you can translate into the others. So for example, if you know how to compute in the ribbon category, then you can take a link diagram, and it will give you an intertwiner from the trivial representation of UQGLN to the trivial representation. That's just multiplication by an element in the ground ring. Well, and that element is just the value of this polynomial on the link diagram. Or if you take the skein module of the 3-ball with empty boundary, then I can look at the tangle without boundary points in there. That's a link. Okay, and then I can simplify that link using these local relations until I have a multiple of the empty link. Well, okay, and the value of that is again this coefficient of the empty diagram, but that's again the polynomial Pn. And there are also ways of going somehow from the skein modules to the ribbon to the morphism spaces of the ribbon category and vice versa. So these are all somehow very closely related. And the interesting thing about these manifold invariants is that they seem to be at the 3-dimensional part of a partially defined extended 4-dimensional TFT that starts in dimension 3, namely with these skein modules, and then goes down in dimension. And at the level 0, it would associate some 3-dimensional category to the point, and that 3-dimensional category is just this ribbon category. That's the idea. Okay, so that's a 3-dimensional warm-up. And now I want to go to dimension 4 and Khovanov homology. Okay, so again, there are 3 sides to the story: link invariants, higher categories, and manifold invariants. And we'll again start at the level of link invariants. The input will be again associated to GLN, namely the GLN Khovanov-Rozansky homologies. For me, these things are functors from categories of links in R3 or S3, and link cobordisms between them to the bounded homotopy category of chain complexes of graded vector spaces. In particular, for a link, this functor assigns a chain complex of graded vector spaces. And if you take its graded Euler characteristic, denoted KhQ here, you recover this polynomial Pn. Okay. If you set n equal to 2, you recover something that's isomorphic to the original Khovanov homology. And the construction of these invariants came from originally from Khovanov and Rozansky, and then the proof that they are functorial was provided in a paper with Michael Ehrig and Daniel Tubenhauer from 4 years ago, and it heavily builds on the technology of foams that was developed by Robert and Wagner. Okay, so that's the input to our construction here, these link invariants, and then we want to construct, so we can ask, okay, is this link invariant somehow governed by local relations in a sense? And is there a higher category that encodes somehow these local invariants? And there is, and this is new, and it's written up in this paper by with Scott Morrison and Kevin Walker. So from the Khovanov-Rozansky link homology, you automatically in the construction get a tangle invariant out, and this tangle invariant can be organized into something that I would informally describe as a ribbon 2 category. So it's similar to the ribbon category that we had before, except that it's somehow 1 dimension higher. You have, it's somehow a braided monoidal, not category, but 2 category. And you could think of it as categorifying rep UQGLN. So this ribbon category from the previous slide. And then once we have this, we can build skein modules. But this time there are skein modules associated to 4 manifolds. And instead of boundary points, I allow boundary links. So a co-dimension 2 submanifold of the boundary. Okay. And then you ask, okay, what's the relation to the original link homology? How can I go back once I've constructed this? Well, if you take the invariant of the 4 ball with a link in the boundary, then you recover the bi-graded Khovanov-Rozansky homology for GLN. And then in analogy to this 3-dimensional skein module picture, we expect that this should somehow form the 4-dimensional layer of this 5-dimensional extended TFT, similar to what I had on the first slide. So it should extend down from dimension 4 all the way to dimension 0, and to dimensions to the point, it would assign a certain 4-dimensional category, and the candidate is this ribbon 2 category. So that is just the outline, and somehow the analogy with the 3-dimensional case. And in the main part of the talk, once I'm done with this introduction, I will talk about these 3 aspects of the story individually. So I'll start with the link invariants, then I'll say a little bit about the higher categories, and then about the manifold invariants. But this is maybe a good place to stop and ask if there are any questions at this point. Doesn't seem to be the case, so but feel free to jump in. So maybe before going on, I should say what this work is not trying to do. But there are many other potential approaches to getting Khovanov homology or Khovanov-Rozansky homology for 3 manifolds or for links in other 3 manifolds. And a priori, what we're doing here is different. So here are a few other constructions that you might, or other routes that you might consider. So one thing is to categorify the Witten-Reshetik and derived invariants of 3 manifolds. So these are numerical 3 manifold invariants, and one could ask whether they can be categorified in a certain way. And the construction of WRT invariants involves somehow specializing the representation category of UQ something at a root to Q, where Q is a root of unity, and then some semi-simplification. And there's somehow lots of technical challenges related to getting to a categorification of these kinds of steps. But there's very interesting math in there. A different route that one could take is to take the 3-dimensional skein modules. So for a 3 manifold, I get a vector space or a module over a ring of Laurent polynomials, and then aim for a categorification of these vector spaces directly to categories, say. And there are different approaches how one could do this, depending on somehow how one would access the 3 manifold, for example, via a Sergi representation or via Hegat splittings. And there are very interesting questions related to either of these approaches. There's also a proposed model for Khovanov homology due to Witten in terms of PDEs in 4 and 5 dimensions. And it's somehow an intriguing question of whether this model extends to, and so these are some of the other approaches that are out there. And just to emphasize that what we're doing here is different. We're not really trying to categorify anything here. We just take the categorified invariant in this link homology and then extend it to a manifold invariant. So I would call this a higher skein module construction. All right.
Paul,
done with it. Yep.
Can I interrupt? Sorry, I just wasn't quick enough when you paused for questions earlier. Would you mind going back one slide?
Not at all.
So, okay, the bottom you said what is supposed to happen when you take the 4 ball with a link in it. You recover something already, right? Do you know anything about what happens if you take, closed manifolds with nothing in the boundary? I mean, with don't have boundary. Do you recover anything already known or not?
Well, Iksho knows better than I, so you should ask him.
I see.
Yeah, no, I'll say a little bit about computations at the very end.
Okay.
But I mean, so even if you don't have a link in the boundary, you do get a vector space here, or an abelian group, or depending on the setup, and it's potentially interesting. Yeah.
Thanks.
Okay, so if there are no other questions, then I think we're ready to dive into more technical things. Yeah, good. Okay, so there will, as advertised, there will be 3 parts: link invariants, higher categories, and manifold invariants. I'll start with the link invariants again. So here is an expanded view on what these Khovanov-Rozansky link homology functors are and how they're set up. So I said they are functors from links in 3 space to some category of chain complexes and chain maps up the homotopy between them. Turns out it's actually not defined on that. Instead, it's defined on a category of somehow a combinatorial model of this category of links embedded in B3. Namely, a category of link diagrams, which model links, and the cobordisms between links are modeled by movies of diagrams. So you just take your embedded link cobordism, you slice it in the time direction, and you look at the slices, and the slices each are encoded by link diagrams. And if you somehow sample that finely enough, then you can reconstruct the link cobordisms up to isotopy from the movie. But there's an ambiguity, and the ambiguity is given by the so-called movie moves of KhRn and Saito. Okay, and the functor is defined from, defined on the source category, these link diagrams and movies of diagrams up to movie moves. And the target is this bounded homotopy category of chain complexes of graded vector spaces. And it turns out that this category really is a combinatorial model of this topological category. So we have an equivalence there. So we may as well consider a Khovanov-Rozansky homology as mapping from there. And the commutativity of the diagram just says that if you start with a link diagram, or if you start with a link with this corresponding diagram, you compute the chain complex, and then its Euler characteristic, then you get the same thing as somehow forgetting from the link to its isotopy class and then computing the polynomial Pn on it. Okay, upshot of this is that if you want to define such a link homology, you have to follow 3 steps. First of all, for each link diagram, you have to provide a chain complex. Second, for every elementary movie between such diagrams, you have to provide a chain map. And then in the 3rd step, you have to do some checks, namely for every movie move. So if you have chain maps for elementary moves between diagrams, then you also know what to assign to a longer movie. You just compose these chain maps. And then the movie moves tell you that some of these chain maps should be related by homotopies. And that's what movie move checks are. Let's look at an example. So here you see a movie of tangle diagrams. There are 4 strands that cross each other in a kind of a half twist fashion. And the 9 pictures, the one on the left is identical to the one on the right. And in between them, you see 8 transitions, and each of the transitions is a Reidemeister 3 move. Khovanov-Rozansky homology assigns to each of these Reidemeister 3 moves a chain map. So to the composite of this 8 Reidemeister 3 moves, it assigns another chain map. But somehow this movie models a tangle cobordism, which is isotopic to the identity. It's really just somehow shaking these strings. And there's one movie move that says that the composite of these chain maps should be homotopic to the identity. Okay, so that's something you have to check in this 3rd step. The good thing is that once you have checked all of these movie moves, then you can essentially consider Khovanov-Rozansky homology as diagram independent. Because diagram independence in the sense that it does not matter which diagram you choose, because whenever you choose 2 diagrams, then you get somehow isomorphic spaces, and every path between them gives you somehow an isomorphism from this one space to the other space, and it actually doesn't matter which path you take because they're all coherent. Okay, so that's somehow the gist of this construction of link homologies via diagrams. You have to do these 3 steps. Why am I recalling this? Well, because if you want a 4-manifold invariant, such that if you take the invariant of the 4-ball with a link in the boundary, and you recover Khovanov-Rozansky homology of the link, then it better be true that this Khovanov-Rozansky homology is an invariant for links in the 3-sphere, not just the 3-ball. Okay, so that sounds like a minor issue, but it's actually quite important. And okay, to see the difference, let's go through the 3 stages of defining the link homology and see if they make sense for S3 rather than B3. Okay, so I think of the 3-sphere as the 3-ball with a point at infinity added. And if I typically, generically, a link in the 3-sphere will be disjoint from this point at infinity. And I might as well restrict myself to the case where I don't hit the point at infinity. So then the link lives actually in the 3-ball. And then I run the usual construction. To that link in the 3-ball, I assign the same chain complex that I would in the 3-ball version of Khovanov-Rozansky homology. So no problem there. Next, we have to associate something to link cobordisms. Now, a link cobordism in the 3-sphere times interval, this is the time interval here, generically avoids the fiber over the point at infinity. Link cobordism is just a 2-manifold and this 4-manifold. Fiber over the point at infinity is just an interval, just an embedded 1-manifold, and generically they will be disjoint. And I might, again, restrict myself to the case where they are disjoint and then treat this as in the 3-ball case. The subtlety arises once we look at isotopies of link cobordisms. This is what usually gives rise to the movie moves. So an isotopy of link cobordisms is something 3-dimensional living in this 5-manifold 3-sphere times interval. And now I have to see whether this intersects the fiber over the point at infinity, which is now 2-dimensional. And here I somehow generically may get some intersections. And those are somehow intersections that I wouldn't see that I wouldn't care about in the 3-ball. And that actually gives rise to a new type of coherence condition that one has to check for Khovanov-Rozansky homologies. And from the perspective of the 3-ball, it looks like this thing here. We call this the sweep around move. And it says that a certain movie of diagrams describes a link cobordism that is isotopic to the identity when considered in the 3-sphere, but it wasn't isotopic to the identity in the 3-ball necessarily. And so from the perspective of the 3-ball, it can be described like this. I have a 1-1 tangle, T, and then the additional arc is closed, and the arc goes very close to that point at infinity. And then it spins around the point at infinity. And that's just a small move. That's just a small isotopy in the 3-sphere. But from the perspective of the B3, it looks like the 1-1 tangle T does the jumping rope thing. Okay, and you can model it as this composition of somehow elementary moves. You first somehow do a Rademeister. You create the Rademeister 1 kink here, and then you have this horizontal piece of strand, and it somehow slides down, and now it's here. And then you undo this Rademeister 1, and now you somehow it's done half of the jumping rope thing, and now it keeps going, and this horizontal arc travels upwards, and then it's there again. Okay, and now
can I ask Paul just to make sure I'm following? So this is a move that what the movie you just drew happens entirely in B3, but the isotopy from this move to the trivial movie is what requires.
Exactly.
Okay, right.
Absolutely, yeah, exactly. So the movie happens exactly. So the movie I can formulate entirely in the B3 setting, but if I want to interpret this as if I want this to be a link homology in S3, then I need to take into account that in the 3-sphere case there exists this isotopy which trivializes this move. Yeah, exactly. And so somehow having Khovanov-Rozansky homology for links in the 3-sphere requires that this move just holds, that the chain map that is associated to such a thing is just homotopic to the identity. Yeah, and that's what we verify in this paper from 2019. So this was somehow, I should say that that Scott Morrison and Kevin Walker have been thinking about these types of invariants for much longer than I have, at least for 10 years or so. But this was somehow the main technical obstruction. to get this to work, this functoriality in the 3-sphere. Okay, there's a slide where I could say a little bit about somehow how to prove this, but I don't think it's I don't think it's essential for this talk, and I might just skip it, but feel free to ask later. Let's go to higher categories. So implicit in the construction of Khovanov-Rozansky homology is somehow a local model for what to do with a crossing. Yeah, so that's a recipe of building a cube of resolutions. For example, for those of you who have seen this before, and it's this exactly the same thing in this GLN homology. And when we prove the functoriality under linked cobordisms already in the 3-sphere, we want to do this locally. That's somehow a strategy that was already advertised very prominently by Barnard in around 2004 in these famous papers. And now I can somehow encapsulate this kind of check of functoriality in this kind of commutative diagram. So I can say Khovanov-Rozansky homology upgrades to a tangle invariant that is this bracket here. Let's call it the Khovanov-Rozansky bracket. And this is now a functor from a category of tangle diagrams, where tangle diagrams are the objects, and by movies of tangle diagrams up to movie moves are the morphisms, to a category that is again a category of chain complexes and chain maps up to homotopy, but this time not of graded vector spaces, but in some other additive category N form, whose precise form won't be relevant for us. Okay, the only thing that might be relevant is that once you take, when you have this category and you somehow form graded Euler characteristic, when you decategorify this, go to the somehow triangulated Grothendieck group, then you recover something like the morphism spaces in the representation category of UQGLN in their incarnation in terms of webs following Kugelberg, Curtis-Kametzer, Morrison, and others. So in some sense, this is a categorification of the Reshetikhin-Turaev functor, or a piece of the Reshetikhin-Turaev functor. Anyway, once you have this, you can assemble this data into what I would call a linear version of a braided monoidal 2 category with duals. Braided monoidal 2 categories have a long and complicated history, maybe starting with Khovanov and Voevodsky, and then iterating through different versions in papers of Bias Neuchel, and Street and Kranz and others. Yeah, and then there are also different notions of duals for objects in such braided monoidal 2 categories, and the thing that somehow works best in the current setting is actually based on a paper by Barrett, Moisberger, and Schaumann. So to get these references out of the way, I should just describe what this thing does. So it's a 2 category, so it has 3 levels of data. It has objects, 1 morphisms, and 2 morphisms. Objects are boundary sequences for tangles. So in this case, I would just say somehow sequences of ups and downs. Okay, like this. 1 morphisms are essentially tangle diagrams. So starting from a boundary sequence at the bottom, mapping to a boundary sequence at the top. And I want to be careful. So I say you just remember the Morse data. You don't actually remember the tangle diagram. And then let's ask what the space of 2 morphisms between 2 tangle diagrams T1 and T2 is. Well, it's exactly the space of morphisms between the bracket invariants of the tangles T1 and T2. So this functor sends a tangle diagram to a complex, and I can look at the chain complex of all graded homs up to homotopy between these complexes. And that's somehow what the space of 2 morphisms in this category is. So in some sense, you can consider this if you believe that tangle boundary sequences, tangles, and tangle cobordisms form a braided monoidal 2 category, somehow the paradigmatic braided monoidal 2 category, then this is somehow a linearization at the top level. So you replace the 2 morphism level by the value of the Khovanov-Rozansky thing on this. Okay. So this is one, yeah, okay. So this is one kind of axiomatization of the kind of four-dimensional category that you can get from Khovanov-Rozansky homology, and you can find this in the last section of our paper. There's also a different model for this four category in our paper. It's using the technology of disk-like four categories. Okay, once you are there, once we have this higher category, we can now ask some questions that will somehow take us towards CFTs. So the idea is that this braided monoidal 2 category should be something like a four dualizable and SO fixed object in a suitably defined 5 category of braided monoidal 2 categories, or E2 2 categories. That's kind of the thing that the cobordism hypothesis would predict as the local data required to build a partially defined 4-dimensional or 5-dimensional TFT like I had it on the first slide, roughly. Okay, so that's somehow the kind of idea. And there's some questions related to this. So for example, what is the role of this sweep around move in terms of the dualizability data of this category and somehow the pivotality data of this category? And can this be made homotopy coherent? Do I really have to take the Khovanov-Rozansky homology as opposed to the Khovanov-Rozansky chain complex? So there are lots of details to sort out, and probably one can get a much stronger result than what we had on the previous slide. But that's maybe a story for the future. What I want to tell you about now is somehow a proposed direct construction for the 4-dimensional part of this theory on the level of homology. And that's somehow what's also in this paper. So the result is that this Khovanov-Rozansky homology controls a disk-like 4 category. And from that, you can define a 4-manifold invariant using the blob complex, which is something that Kevin and Scott have developed some time ago. And this would be, so in general, this will be a triply graded abelian group, or if you work over a field, it would be some triply graded vector space, where one grading is the quantum grading that corresponds to the Q in your linked polynomials. One grading is homological in nature, and it somehow decategorifies to -1 in the Euler characteristic. And then there's an additional grading, which is the blob degree, and it's some kind of a derived degree. It's something like the degree when you compute Hochschild homology. And to simplify things and actually get to something that can be easily somehow has a chance to be computed, I want to restrict to degree 0 blob homology, because this has this degree 0 blob homology part of this invariant has a description in terms of a skein module. Okay, so I want to refer back to the 3-dimensional motivation. So there, the skein module for 3-manifold with some set of points in the boundary was defined as the quotient of the 3 modules spanned by framed oriented tangles. And the relations came from the local relations satisfied by the knot polynomial. And a little bit more intrinsically, I can describe this as the kernel of the Reshetikhin-Turaev functor. Reshetikhin-Turaev functor somehow sends tangles to morphism spaces in the representation category of the quantum group UQGLN. And in particular, it sends tangles to elements of a vector space. And I can ask what sort of formal linear combinations of tangles get sent to 0. And those formal linear combinations of tangles are exactly what sort of relations you impose in the skein module in a local way. And motivated by this, we would like to be able to define the skein module of the 4-manifold with a link in the boundary as, well, we form a free module, a free abelian group spanned by framed oriented surfaces in the 4-manifold with boundary that link. And then we mod out by the local relations that are satisfied by the Khovanov-Rozansky bracket. Okay, that's somehow the exact analog of this construction up there. You take somehow the topological top-dimensional thing that your invariant sees and sends to a vector space, and then you mod out by relations, by local relations in the kernel of this evaluation. Problem is, it doesn't quite do what we want. So if we want the invariant of the 4-ball.
Paul, can I ask a question?
Yeah.
This can be any 4-ball inside W?
Yes.
Okay.
I mean, smooth and oriented,
Right.
embedded. Yeah. Yeah.
But it's just,
Any
like
4-ball.
a skein relations, like I choose a 3-ball and I
Yeah.
Okay.
Yeah, I mean, this space is huge, and these relations are, I mean, it's a huge thing. Yeah. Yeah, any embedded 4-ball. Okay. Yeah. So I should say that this naive thing doesn't do what we want. So maybe the only expectation that I tried to raise was that when you take the 4-ball with a link in the boundary, you should recover the link homology. But this would require that the homology of any link is spanned by the image of cobordism maps from the empty link, and that's just not true. Okay, so somehow these skeins are not big enough to somehow span these skein modules where we already decided what we want. Okay, so to get this to work, it's not enough to consider these surfaces in the 4-manifold. We need to use some kind of decorated surfaces in the 4-manifold. And somehow in the next few slides, I want to make precise what these decorated frames-oriented surfaces are, somehow what the skeins are in this Khovanov-Rozansky skein module.
Hey, Paul, this is Melissa. I'm just wondering, topologically, what does it mean that not all links, or maybe framed links, are spanned by images of cobordism maps from the empty link? Like, is there something obvious topologically that I'm missing?
No, I don't think so. I mean, I think it's just if you, for example, if you consider the Hopf link, I mean, there's some classes in the Khovanov homology of the Hopf link that you get by somehow looking at images of certain annuli and this sort of stuff, but you don't get everything.
Yeah. Oh, sorry. Okay, so you mean like the classes of the actual homology?
Exactly.
Okay, that makes sense. Thank you.
Yeah. It just gets worse, I think. Okay, so what are the skeins in the end? So they're called lasagna fillings. I should explain the name. So this comes out of somehow the subfactor tradition, where one works with planar algebras, and for planar algebras, people have this image in mind of somehow spaghetti and meatballs that are arranged on a plate, and you can move them around. Okay, so this is somehow the 4-dimensional version of this, and instead of spaghetti, you have lasagna sheets filling your 4-dimensional plate. Okay, what are these? So I mean, I've tried to schematically indicate. So this is the 4-manifold here, the entire thing. I use this pen. So this is W4. On the link of the 4-manifold, I have on the boundary of the 4-manifold, I have a link L, which is this piece here. And then I have a surface somehow in the interior. That's a sigma. But there should be these additional decorations that I've mentioned, and they take the following form. So I'm allowed to drill out a finite number of 4-balls from the interior of the 4-manifold. And I'm allowed to decorate the boundaries, the newly created 3-sphere boundaries, with links Li. So I'll say that they are input links, and I say they lie on these input spheres, and it will be clear why I say that on the next slide. And then the surface should be framed, oriented, and embedded in the 4-manifold minus these 4 balls, and intersect the boundary transversely in exactly those links. So there's some outer boundary, which is this given link L, and there's some inner boundary on these newly created drilled out 4 balls. Plus some additional information, namely, each of these input links has to be decorated by a Khovanov-Rozansky homology class of that link. Okay, and well, these links live in the boundaries of these 4 balls, actually in the boundary of this 4-manifold minus the 4 balls. So in particular, they live in 3 spheres. So we know what these Khovanov-Rozansky homology classes should be. I mean, we know what Khovanov-Rozansky homology in 3 spheres is. Okay, that's the sort of that's what a skein is. Next, I have to describe to you what sort of skein relations we consider. To describe what sort of skein relations we consider, I have to use the notion of a lasagna operad. I would like you to focus on the picture on the left for now. So this looks a bit like a lasagna filling of a 4-ball. So I have a big 4-ball, and then I have some smaller 4 balls drilled out. So on the outer boundary, I have a link L. On the inner boundaries, I may have some links Li. And then in the complement, I have the surface sigma, which connects these links on the outer boundary and on the inner boundary. Such configurations, I claim, form a colored operad. So the colors of the operad are links in 3 spheres. And whenever you have somehow 2 compatible such pictures, and one of the pictures has somehow an interior boundary, you can shrink the other one and glue it inside. And that gives somehow a composition operation in an operatic sense, in a colored operatic sense. Okay, now I'm claiming that Khovanov-Rozansky homology gives an algebra for this kind of operad. That means for every color, that means for every link in a 3 sphere, it assigns a vector space or a greater abelian group. Well, these are just the link homologies of these links. And then for each of these configurations that we call lasagna diagrams here, it assigns a linear map or homomorphism from the tensor product of the input things to the output thing. And it does so in a way that is compatible with this operatic composition. So if you have 2 pictures and you shrink one, put it inside the other, that's like a contraction of tensor contraction of linear maps. I think I have enough time to sketch how one proves something like this. So basically, yeah, for every such diagram, I have to create a linear map. Let's first consider the case where I have a single ball on the inside drilled out. In that case, the complement will be diffeomorphic to S3 times an interval. And I have a surface sigma in S3 times interval connecting 2 links. And I have to find a linear map associated to this. But that's exactly what a link homology does. Right? It's functorial on the link cobordisms. The problem that we're facing here is that you might have more than one of these input spheres. And so we want to cheat and we want to say, you can always turn this collection of such input spheres into a single input sphere. And we do this by you choose a tree in the complement, and then you drill out a neighborhood of that tree, and that tubes the spheres together and creates a single sphere where these links now are somehow split disjointly embedded, these input links. And then we use somehow the lax monoidality of Khovanov-Rozansky homology to give us a map from the tensor product of the Khovanov-Rozansky homologies to the Khovanov-Rozansky homology of the disjoint union, and then we use the usual functoriality. The issue is just when you tube these spheres together, you've made a choice. You've made a choice of this somehow tree that you drill out, and you have to study what happens when you isotope this tree around. And there's one interesting thing that can happen, namely the tree, as it moves, could collide with the surface sigma. And so we have to study what happens there. And it just turns out that the local model for this interaction is again given by the sweep around move that I had a few slides prior. Okay, so somehow, since we already know that the sweep around move holds in Khovanov-Rozansky homology, that problem is taken care of. And there's somehow a coherent, you can move this tree and you get just a coherent isomorphisms between the results. That's kind of nice. And maybe this is also a good point to remark that you can play this construction, not just for Khovanov-Rozansky homology, but basically for every link homology that is functorial in the 3 sphere, at least laxly monoidal under disjoint union, and satisfies the sweep around move, because those are the only properties that we're using here to set up this kind of lasagna algebra thing. Okay, let's say for now that maybe we believe that the Khovanov-Rozansky homology gives us such an algebra. What can we do with it? Maybe I should remark the following. Let's compare the notion of such a lasagna diagram with the notion of a lasagna filling for the four-ball. And if you remember back on the previous slide, I've defined what the lasagna filling was, and it looked very similar, except that I allowed general four manifolds and I put these vectors on the input links. Now, let's suppose I have a lasagna filling of the four-ball. That's just the same thing as a lasagna diagram in the four-ball, plus a collection of vectors for each, a Khovanov-Rozansky class for each of these input links. Okay, so, and now I can do the following thing. I know that the lasagna diagram for the four-ball gives me such a linear map, Khovanov-Rozansky of the diagram, and I can just feed in the tensor product of these labels that the lasagna filling gives me, and I recover a single Khovanov-Rozansky class for the link on the boundary. Okay, so if this comes with vectors v1, v2, v3, I plug them into this linear map and I get a vector v out here. Easy. I'll remove this again. Okay, and that we use on the next slide to define what the skein relation is and what the skein module is. So we take the skein module to be the free abelian group spanned by lasagna fillings of the four manifold relative to the link, the fixed link L. And then we say the skein relation is generated by the following equivalence relation. Given a lasagna filling, I can choose to drill out a larger four-ball. Okay, and drilling out such a larger four-ball, on the one hand, gives me something like a lasagna filling with the larger input four-ball. And on the other hand, on the inside here, I see a lasagna diagram plus some vectors vi. And now I take these vectors vi and feed them into the Khovanov-Rozansky map that I associate to this lasagna diagram inside the four-ball. That gives me a vector v. And now this is the vector that I have to plug in here so that, that these things become equivalent. Okay, so that's the kind of way that we model the notion of being in the kernel of the Khovanov-Rozansky functor. That's somehow what makes this rigorous. Okay, and then a few comments. So this thing will have three types of gradings. On one hand, there will still be a Q grading. There will still be a homological grading. And now there will also be a grading by the integral second relative homology of the four manifold rel the link, because every lasagna filling represents such a homology class, and the relations that we impose here are homogeneous with respect to that. Maybe I should say, if you want to, so this uses an oriented version of Khovanov-Rozansky homology. If you're used to Khovanov homology, then it's sometimes you're using an unoriented version. Then in this case, you could try to do something similar, but you would only get somehow a grading by homology with set mod 2 coefficients, I think. So somehow here it's nice that we get integral coefficients. Okay, and then now let's maybe think a bit about how this relates to four manifold topology. So there were recently some results that you could interpret as somehow restricting the size of these skein modules. So Goodrow and Levine showed last year that Khovanov homology is insensitive to the tangling of cobordisms between split links. So if you have a link cobordism somehow that consists of a number of components, and that the components somehow map from a link that is somehow manifestly split to a link that is manifestly split, then you can compute the linear map induced by just computing them on the individual components and ignoring that they're tangled. So that somehow says that they are under the equivalence relation of somehow being sent to equal maps on the Khovanov homology, these two cobordisms could not be distinguished, and so they cannot represent different classes in the skein module S0. There are also results that by Sundberg and Swan from this year. It says that Khovanov homology is insensitive to local knotting, so insensitive to somehow connect summing with a knotted two-sphere. Again, somehow, if you don't know this, then you might think that they represent different classes in the skein. Somehow there are lasagna diagrams or lasagna fillings that differ by connect summing locally with a knotted two-sphere. Well, it turns out that Khovanov homology doesn't see the difference. And so they're modded out by this equivalence relation. So this is kind of interesting. I mean, these results are formulated for Khovanov homology, but I mean, I would expect that they also hold for Khovanov-Rozansky homology. So this is some indication of somehow what this might be able to see about smooth surfaces in four manifolds. Okay, and then somehow ongoing work towards an application uses that these link homologies admit deformations. I like to think about this from a representation theoretic perspective. So there's GLN, and inside GLN you have the product of GLNIs, subly algebras, where the ni's are just somehow non-negative integers that sum to n, or positive integers that sum to n. And whenever you take such a decomposition of n, then you get an induced spectral sequence from the Khovanov-Rozansky homology for n from a given link to something that is somehow parameterized, some deformed version of Khovanov-Rozansky homology, which is somehow parameterized by such a decomposition. And it turns out that this thing is somehow abstractly isomorphic in a filtered way to the direct sum of the Khovanov-Rozansky homologies with respect to individual ni's. And we can also build skein modules in this theory. So somehow for this deformed stuff. And if you set all the ni's equal to 1, then you recover something familiar, namely somehow the Lie version of Khovanov homology or the Gornick version of Khovanov-Rozansky homology. And in some sense, that allows you to somehow break the Khovanov-Rozansky homology, which might be very complicated, into small manageable pieces associated to GL1. And that somehow explains, this representation theoretic picture explains why you deform GL2 into GL1 plus GL1, and that somehow it corresponds to the fact that the Lie homology of a knot is two-dimensional, one for each GL1. Okay, and then somehow from these deformed skein modules, the expectation is that you could get something like Rasmussen invariants for smooth surfaces and one for each relative second homology class. Not done yet, but that's something that might be possible. Okay, and at the very end, okay, so a few examples. Well, for the four ball, I've already mentioned the skein module. So I've somehow suggested this, but I haven't stated it yet, that the skein module for the four ball with the link in the boundary is really isomorphic to the Khovanov-Rozansky homology. And it turns out that actually the whole block homology is isomorphic to this. Maybe the next simplest example is if we consider 3 ball times S1 with a link in the boundary, then we do expect that this is related to Rozansky's invariant for links in S2 times S1, although not identical. So they're probably related by a spectral sequence. And the coolest computational result about these skein modules you'll actually hear in the next talk. So I won't say much about it, except that it's about somehow two handle bodies. And I think this is a good place to stop, and I thank you.
Great, thanks, Paul. Let's give him a round of applause. All right, any questions? You can just unmute yourself and ask.
Hey, Paul, I have a question. This is Melissa. Sort of related to Dave's question during the talk, and also when you said that as you can play this game with anything that has these 3 properties. How related is the sweep around move to just the neck passing relation that Sung-Kyung Kang wrote about in his ribbon obstructions paper? So it's just two very simple version of your sweep around, right? Where the tangle is just not a tangle, like an identity braid. I wonder if there's a way to sort of reduce your tangle to these pieces and then just say that this is equivalent to sweep around, in which case everything that was in Adam Saltz's paper would follow this. They're definitely monoidal.
Yeah, that's a cool question. I do remember that somehow when Scott, Kevin, and I started talking about this, that they had some idea to prove the sweep around move using that kind of ideal. It then happened that somehow we wanted to do this somehow for the GLN story, and there this kind of reduction didn't seem to somehow be that promising, but it might be that it just works in the in the Khovanov homology case. It's just that somehow, if somehow you really want to somehow follow this route, you should work with the functorial version of Khovanov homology. And then somehow my inclination would be always to go somehow to the Blanchet version right away, where you work with forms, and then you again, then it's not so easy to implement the strategy again. But you might somehow look at a different fix of functoriality for Khovanov homology, and then maybe this somehow is another approach towards the sweep around move. Yeah, well possible.
Okay, so it sounds like anything I'm working with that's like, this is more of like a rank 2 shadow of your sweep around move.
It may be, it might also be that it generalizes, I don't know.
Okay, thank you.
I have a question. This is just vague, but you said at the beginning that in some sense you expect this is really like a 5-dimensional theory, right? Do you have any intuition what that means in like what's going on 5-dimensionally? If that makes sense at all, like is there any information?
Yeah, I mean, somehow, well, I guess the intuition starts with somehow say your 5 manifold is very thin. It's like it's like a 4 manifold with times epsilon, an epsilon thick interval, and you only look at somehow you do get maps for 5 manifolds, but maybe only for diffeomorphisms, as the traces of diffeomorphisms of the 4 manifolds. So that we do have, yeah. And then you could ask, okay, so maybe I should somehow study the extension problem to a 5 DTST, somehow one type of 5 handle at a time, or somehow 5-dimensional handle at a time. And then I think you could say that somehow some 5 handles, for some indices do exist. So for example, for the 4 sphere, the skein module is isomorphic to the ground ring. And you could interpret that as somehow the identification of the 4 sphere skein module with the ground ring, which is the skein module for the empty manifold, as being the thing that's somehow mediated by the index 5 handle or the index 1 handle, depending on which way you count.
Great, thanks.
I had a question. I think you had this example of an isotopy of cobordisms that was trivial in S3 but non-trivial, or trivial in S3 cross I squared, but not in B3 cross I squared. Is that that's how I understood it?
Yeah, exactly. It's this thing here.
You say it's a new movie move to check. Is it clear that this is the only?
I think you have to give an argument. I think you have to give an argument, and we do in the paper. There might, I mean, one other way of viewing this is just saying that, okay, try the following. Suppose you already know what it means to compute Khovanov homology in an abstract 3-ball. And now say we want to do this in the 3-sphere, then somehow I have to choose a base point to take out of the 3-sphere. And then I know how to compute the Khovanov homology. And then I somehow need a coherent system of base point moving isomorphisms. And somehow, then you somehow use that the pi1 is generated by meridians. And somehow when you move the base point around the meridian of the knot, somehow the point to take out, then you will see such a move. And that's maybe one intuitive argument for why this is the only one. Caveat, this is actually not a single movie move in the classical sense, because somehow you have to check this for every 1-1 tangle T, which makes this so complicated. And there's no bound on the complexity of what such a computation actually entails. So you cannot detect this with brute force in the same way as you can attack the other movie move checks using brute force.
All right, thank you.
All right, so let's thank Paul again.
Thank you.
Great. So I'll stop recording.